Welcome everyone to this yet another video on DSA in JavaScript. In the last few videos we have been talking about the recursion. We have understood what recursion is. We have talked about that how do we find time complexity in the recursive function. Now it is a time to dig deeper. Why do the recursion behaves differently than the loops? What is that which powers recursion to move in both the directions? And also we talk about the different types of the recursion and few problems around it. So now let's get started and go deeper into the field of the recursion. So let's get started with the very first recursive problem and we'll try to see that how it gets getting executed internally. So let me go and open my code, and here let me go and let's say that I want to, let me go and open my scribble, and what I want to do is that let's say that I have an array that looks something like this, 3, 5 and 7. I want to go and print the element of this array in the reverse order. We have already seen the recursive code for the same in the past classes. Please pause the video and quickly write the code so that you are feeling comfortable about writing the code in the recursion. So now let's try to do it ourselves here in this video. So what we do is that let me go and define a function. I go and call it as function, and I go and say that print, and then I go and pass array, and then I go and pass the starting index. We have already seen this code. I'm not going to spend much time here. Now if it is a recursion, the very first thing that we need to do is that we need to go and provide base condition, right? In the base condition I go and write if starting index is greater than equals to array.length. In that case what I go and do that I don't do anything, I just go and return. Otherwise what I say, I go and call this function recursively, print array, and then I go and increase the index by 1, and then I go and call this, I go and say that console.log, and I go and pass array si. Fair enough. So I have written this function that which you are seeing on the screen right now, right? Let me go and call this function. So I go and call it as print, and inside this I go and pass an array like 3, 5, 7, and I go and pass the starting index as 0 itself. If I go and run this, right, if I go and say that node rec part1.js, it is printing 1, 5. Sorry, I just ran the wrong file. If I go and say run recursion part2.js, part1 was the previous session, go ahead and enter. It is giving me certain errors. What is that? Where am I? I'm inside this folder. Let me see the path, pwd, and inside this I have this file. Okay, this file I have defined wrongly somewhere. It is outside this, so what I have to do, I'll have to put inside the recursion folder. So this is the folder in which I have been writing the code. And again, a good learning for us, if I have to go and execute a JavaScript file using the node.js, I have to go and provide the correct file. I'm purposefully not editing out this portion because these kind of errors do happen, and I want you people to know that if this happens, you don't have to feel bad. You have to go and find the root cause and fix it. Now since I have put that into the right folder, now if I go and run this code, node recursion part node rec, and then it is part2.js. If I go and run this, I'm able to print 753. Perfect, simple question. It just took us some little time, but I'm not editing out this. Now let me go and copy this whole code and paste on my system, right? So I go and paste it like this. Now let's try to see that how this code has happened. Let's try to do a quick dry run of it. So when I go and do a quick dry run of this, I go and say that hey print, and the print I go and pass this array as 1, 2, 3, and I go and pass the starting index value as equals to 0. So the first time when the function is getting called, at that time the value of array is equals to what? The value of array is 1, 2, 3. What is the value of starting index? The value of the starting index is 0. So starting index value is 0, this value is equals to 3. Is it true? No. So it comes here and calls the function recursively. So this calls the function recursively second time. Array value is equals to how much? 1, 2, 3. Starting index value is equals to 1. This is all which has been already told to you people. I'll quickly move through. Here again, next time when the function is called, starting index value here is 1, this value is 3, doesn't hold true, so again the function is called recursively. Third time, array remains same, which is 1, 2, 3, starting index value is equals to 2. So the next time when the function is called, this value is 2, this value is 3, does not hold true, I again go back. Next time when I go back, fourth time, array value is 1, 2, 3, starting index value is equals to 3. So the last time when it is called, right, the SI value has become equals to 3, this value is also equals to 3, holds true, so I go and return. So this is where the base condition hits. And from here it comes back to the step number 3. When it comes back to the step number 3, it finds that at this point of time, SI value is equals to 2. So it goes and prints the element at the second index, so it prints first of all 3. Then it again goes back, it goes and prints the element at the first index, so it prints 2. And it again goes back and prints the element at the first index and print 1. Quick revision, we know that in the case of the recursion, when I move from the step 1 to the step 2 to the step 3 to the step, let's say that base condition, right? You first move here, you move to the last, then you base condition, you come back, and then only you finally terminate. So in the case of the recursion, you only terminate at the end. And it moves in the complete loop. You move from left to right, then you again come back right to the first position itself. How is this happening? What is enabling us to achieve this? This is happening because of a concept called as stack. Now, stack is the data structure that we're going to learn in details in the future lectures. But as of now, try to understand stack is a kind of a data structure which believes in the principle of first in, last out, or you go and say that last in, first out. Think of an example. Let's say that you go to a restaurant. In the restaurant, when you see that all the plates are kept, so the first plate which is kept goes in the bottom and the last plate which is kept goes at the top. So if anyone has to pick up any plate, which is the plate which was picked first? The one which was kept the last. Fair enough. That's what typically a first in, last out, or last in, first out data structure, and stack provides that. Now, so far what we have been saying that in the recursion you move from the step 1 to step 2, step 2 to step 3, step 3 to step 4, and after you hit the base condition you come back. This all thing is possibly happening because of this data structure called as stack. How does that happen? Let's try to understand in the detailed manner. So let me first of all go and copy this code. So I have copied this code. Let me take it to the next page and paste it here. Fair enough. Cool. Now what happens every time you try to go and execute a code in the recursion? Every code that you go and execute, something called as a call stack. Call stack gets created. Or sometimes you also go and call it as a function stack. Before the function is executed, initially the call stack is in the state called as empty. Fair? Now as soon as you go and execute this function, you go and call it as print and you call it like 1, 2, 3 and you go and pass this starting index value equals to 0. As soon as you go and call this, one entry in this stack gets created. When you insert something into the stack, you go and call it a push operation. And in this push operation, you go and say that, hey, you know what? There is an array value 1, 2, 3 and there's a starting index value which is equals to 0. You go and store it. Now then again, you go and call recursively from here the another function, print, right? So what happens? From here when you go and do, this value is equals to 0, this value is equals to 3, does not happen, so you come here. So again this function is called recursively second time, print 1, 2, 3 and the value is equals to 1. Again what happens in the call stack, this entry gets pushed. So you go and say that another entry is formed where you go and pass the same array 1, 2, 3 and starting index value that is passed is equals to 1. Then again, what happens? The value is 1, this value is 3, doesn't hold true. So again, you go and call this function recursively third time. Third time when the function gets called recursively, you again pass print, you pass 1, 2, 3, and starting index value is equals to 0. You again go and push, right? And this is the entry. And then you go and pass what? 1, 2, 3, and starting index value that you go and pass is 2. Clear till this point? Great. So what you see here, as soon as you keep on calling the function and function is not done executing, it is there inside the call stack. Then again, the next time you go and call this function and you go and pass print 1, 2, 3, and like this you go and call it. So again, the third time the starting index value is equals to 3. This is 3, this is 3, so you go and return. So when you go and return, right, you have nothing to do now, right? So you come back to, you don't have to push anything, you come back here. When you come back here, you have to go and, so at this point, position of time, when you are here, right, the value of SI is equals to 2. And then you go and print array SI. So array SI value you go and print as 3. And then this function is done executing. So when this function is done executing, what you do is typically you basically pop it out. So to pop it out, as soon as it gets deleted from the call stack. It gets deleted from the call stack. Now again it goes back to next step. I'm maintaining this state, SI is equals to 1. Now SI value is equals to 1. Again what happens? This line of the code has to be executed. So one index value is what? It is equals to 2. So I go and print 2. Now this function is also done executing. So whatever, I'll have to pop it out. So when I pop out anything from the stack, pop means to remove anything from the stack. This entry also gets deleted. And then finally, I'm back on this stage. At this point, the value of SI is what? 1. One value is equals to 1. I go and store it, and then this also is done executing, and again I pop it out. When I go and pop it out, my stack is now fully empty as it was before, and I'm done executing. So it is the stack data structure which is internally being used by the recursion to solve any problem. So the point that we get from here is that anytime you go and make use of recursion, I said that recursion makes things easy and intuitive, which I'm going to prove in the coming time. But the recursion comes with a cost. Any recursion that you use, it internally uses stack data structure. And since it internally uses stack data structures, it has a space complexity. So given a chance, if a problem could be solved by both recursion and iterative, normally iterative is considered to be more space optimal, because by default, if it is a recursive problem, it will internally make use of stack, which is an extra storage. So recursion has high space complexity compared to loop. So same problem, boss. If I have a problem and I know that this problem could be solved using recursion also and through the loop also, normally I'll go and give the preference to the loop because recursion has higher space complexity. But recursion comes handy at the places where typically solving the problem through loop is almost very complicated or tough, and that's where the recursion comes handy. So there is certain trade-off. You don't get everything everywhere. To get something better, you have to compromise at certain places. Now since we have understood that, now let's try to move to the next topic, which is, now there are multiple types of the recursion. We are not here to pass our semester examination. So we'll talk about which is important from the interview perspective, or which is needed for your day-to-day work in the professional world. So from that perspective, there are two types of recursion which you should be aware of. Recursion. And what are those two types of the recursion? The one type of the recursion is called as tail recursion. And other type of the recursion is called as the head recursion. And I'll put the statement first. Normally, tail recursions are said to be better and more space optimized compared to the head recursion. I'm putting the statement first. Normally tail recursion is said to be better time optimized, better space optimized than the head recursion. Why it is happening, we'll see now. But this is a very important question. When I was asked, when I was interviewing for Amazon, this question was asked in my first or second round. Exactly, I don't remember, but this question was asked from you. So first of all, let's understand what is the tail recursion, what is the head recursion, and then we see that why we say that tail recursion is more space optimized. So tail recursion, if I go and talk about the tail recursion is a kind of a recursive program in which recursion is the last step. I always told you that whenever you go and call a recursive function, there has to be a base condition, there has to be the logic, and there has to be the recursive call. When this recursive call is the last step, that typically is called as a tail recursion. On the other hand, a head recursion is the one in which after recursive step, after recursion, there is a logical part. So if there is a logical part after the recursion, then that typically is called as a head recursion. Let's try to see that with the help of a code example. Let's try to move on. So I came back to my code here, right? And let me go and comment this print portion. Take an example. So let's say that my use case is to go and print the numbers starting from n and it goes down. Okay. So what I go and do here is, let me go and define a function called as function print n, and I go and pass number n here, and I go and say that if n value is greater than 0, then I go and pass the logic, which is console.log print n, and I go and call this function recursively print n minus 1. Let's try to run this. So if I go and do this print n and I go and pass here 5, let's try to run this. It is printing 5, 4, 3, 2, 1. Okay, my code is working perfectly fine. Now if I go and try to analyze this function here, right, if I go and try to analyze the problem here, if you see here in this case, this is my recursive call, right? And this is the last step also, last step. So when I go and call this function, say for example, print 5, or let's say that, let me call a smaller number like print 4, right? What will happen? It will go and call print 3, it will go and call print 2, it will go and print 1, it will go and print 0. And same thing in the stack, call stack, if I go and see, it will go and first of all go and store the value here as n value is equals to 4. The next time when it is called n value is equals to 3, n value is equals to 2, n value is equals to 1, n value is equals to 1, 0, right? Like this it will try to be called. Now since the recursion is the last part, right? When I'm coming back from here, I'm not doing anything, Since recursion was the last part, I'm not doing anything. When I come back, I'm not doing anything. We can do some kind of optimization. I don't need to go and store the value because I don't need to use it later. If you see in the previous case, right, in this case, right, I have to go and store the values of this 3, 2, 1 because when I'm coming back, then I have to print. But in this case, since when I'm trying to come back, I'm not doing anything. I'm just jumping and coming out. I don't need to store that state. So when I go and write the code in this manner, I can do some kind of space optimization. On the other hand, if it is a head recursion, right, if I go and do my code and I make the changes in the same code like this, if I take this step above, right, and I try to execute it, right, if I go and write the code like this, and I call this function recursively now, right, if I go and call this function print n3, what happens when it calls n value is equals to 3 and then it calls recursively again, it calls print 2 where n value is equals to 2, print 1 and where n value is equals to 1, and then print 0 and n value is equals to 0, and here it hits the base condition, it's come back again. Now when it comes back again, it has to go and print this, so I have to somehow in my call stack I have to maintain n equals to 3, I'll have to maintain n equals to 2, I'll have to maintain n equals to 1, I'll have to maintain these values, because when I come back I have to run this, because I'm doing the operation of console when I'm coming back. Are you getting my point? So when it is a head recursion, when I'm coming back, when I'm trying to pop out the functions from the call stack, I need to store that state so that I can do those things, and that's why this requires the state to be maintained, and that's why it has a higher space complexity. Space complexity remains same only, but like in the case of the tail recursion, I can make it more space optimized. So normally people will ask you the question between the tail recursion and the head recursion or non-tail recursion, which one is better? You should always try to write a tail recursive code, because then certain optimization could be done there. Fair enough. So now we have done a good amount of understanding in the recursion. We have solved several problems. Now our approach should be that as we make the progress, every problem that we try to solve, we'll try to see both from the iterative as well as the recursive angle. But before we move to the next topic, one final ultimate question which I feel that everyone should master, and if you are able to solve this problem, you can think that you have a good hold on a recursion. Let's try to solve that problem. Solve it with me. If you are able to solve it yourself, great, you have a very good hold on recursion. If not, don't worry. Most of the people that I have taught, they have never been able to solve this problem themselves. But what we'll do is that we'll try to understand this well, grasp it well. Even if you're not able to solve this, okay, try to solve with me. And then what you do, every time you find a problem which is very difficult to solve, make a note in a separate notebook. Try that question every 7 days. So let's say that you have done it today after seeing this video. Note that down because you have not been able to do it yourself. After 7 days, try that question again. Then again, try the same question 14 days post that. There will be certain question which you will have to master it like this. And the next question is definitely of that type. And that question is called as Tower of Hanoi. It's a very famous puzzle. What this puzzle says that, the puzzle says that there are 3 towers. I'm just going to explain you the problem and I want you guys to solve this problem. The next video which I go and upload, I'll provide the answer also, right? But I'll give you the hint. The power says that there are 3 tables, right? So let's say that there's a table 1, there's a table 2, and there's a table 3. And then there are coins on the top of it. Now there's a condition. The condition is that how the coins are kept, only the smaller can go over the larger coins. That's number 1 point. You cannot keep the larger coin on the top of the smaller coin. And number 2, all coins are arranged top to bottom in increasing diameter. Obviously, because first point implies the second point. That's number 1 condition. Your ultimate goal is that this is the initial setup, that's number 1. You have to move this setup like this. Finally, all your coins which is there on T1, T2, and T3, all your coin on T1 should actually move to the T2. So now nothing should be left on the T1 and all the coins should have moved to the T2 like this. In order to do this, there's another constraint that at a time only one coin can move. You have to tell me how much steps does it take to move all the coin from the T1 to the T2. I'm again repeating. There are three tables, table 1, table 2, table 3. Table 1 has n coins. The coins are kept in the ascending order. It's a rule that only a smaller coin can sit over a bigger coin and not the vice versa. You cannot put a bigger coin over a smaller coin. It's a rule. And the second rule is that at a time you can only move one coin, boss. Now if I want to move all the coins from the table 1 to the table 2, in this situation, how many steps do I need to take? Let's try to understand with the help of an example. Let's say that I have the case 1 where there is only one coin. This is table 1. This is a table 2, this is a table 3. Very simple. In that case, I'll directly move this coin from here. So number of steps that will be needed is equals to 1. Perfect? Awesome. Let's do the another case where n value is equals to 2. If n value is equals to 2, what happens? This is the table 1, this is the table 2, this is the table 3. Initially, you have one small coin, bigger coin. Table 3 is your helper coin. So what you do first is that you can move this coin to table 3. So this is one step. When this happens, the whole situation looks like this: T1, T2, T3, and right now this smaller coin is here and the bigger coin is here. What you can again do is that you can move this coin here. So this will take one step. So now again the situation goes like this: T1, T2, T3, and the bigger coin is here and the smaller coin is here. What I need to do, I can again go and move here. This will again take how much? One step. And if I go and do this, finally the situation looks something like this: T1, T2, T3, and then I have this bigger coin and then I have a coin on the top of it. So total number of steps is equals to 3. Now the question is, when I had one coin, I took one step. When I had two coins, I took 3 steps. How many steps will I need if there are n coins? Now I want you people to apply all the recursive concept that you have thought so far. See, the trick here is not to get the answer. I'm not expecting you to get the answer. So please don't Google. If you have not solved this problem previously, please don't Google. You will find this question everywhere. The intention is not to find the solution. The intention is that you should try to sleep with this question. Sleep with this question. And what is the meaning of sleeping with the question? Meaning of the sleeping with the question is that try to work hard. You have to make your brain. See, one of the biggest problem or challenge that I see the people face is, what they do is that they try solving a problem. They try it for say like 30 minutes, 40 minutes. And if they're not able to solve it, they go and Google it. They go and do the chat GPT. And then they find the solution. They feel that, hey, it's easy, I can solve in the interview. This is one of the biggest mistakes that you people are doing if you are applying this. As soon as you inculcate the habit of seeing the solution, your brain is very smart. Your brain will understand that my boss always looks for solution. If I keep on waiting for 30 minutes, if I keep on behaving like a layman, a stupid person who doesn't know anything, my boss will go and see the solution over the internet. And if you once start inculcating this habit, you will never be able to solve the problem. In these sessions, my whole intention is to train your brain so that you can think about the complex problem. That will only happen if you start struggling with the problems. It's okay if it takes you 2 days, 3 days, 5 days, but keep on struggling till you find the solution. At least give it 2 days of time. So till the time the next video comes, if you are able to solve, great, put that into the comments and tell me that you have been able to solve it. Tag me over the link and it will help you give some kind of accomplishment. Even if not, I'm very happy. But I want you people to keep on trying. In the next video which I upload, it will get started with the solution of this problem. Keep on watching the videos. Keep on showering the love. I want your little support so that this channel grows a little faster so that I can bring more content, more videos. This whole JavaScript stack is now only DSA, but we'll move to the advanced DSA, full stack development, anything and everything which is around the JavaScript. And similarly, I'm planning to start an AI track in Python. So keep watching, keep loving. Thank you everyone for watching this video.